So in today's video, here is a nice problem regarding arithmetical number theory. Here is the following setup. For all n as a natural number, we have this statement: n squared plus n minus number 1, quinary square plus number 1. Okay, so our goal, we are going to prove this setup is not a perfect square. Okay, so usually the proof is coming as a perfect square, but this time is coming in the opposite way. Okay, so now anyway, we are going to check. Now, by the way of contradiction, we are going to assume this one is a perfect square. At the end of the term, we will find it's impossible to be a perfect square. Okay, so let's go through this one to see what's given us. So we're saying this, the whole term is a perfect square. It will be written on this form. So by the way, contradiction, suppose this quantity n squared plus n minus number 1 quinary square plus number 1 equals x squared. Okay, so I have 3 whole squares here. Now I'm going to transfer this one into one square and expand this one first. I get n squared plus n squared from here. I get 2 times n squared. I get minus 2n here plus number 1 plus this number 1, which is plus 2. Okay, the whole thing equals x squared. Now I'm simply, I see number 2 everywhere. Now I'm going to take number 2 as a common factor. Let's put it in this way. Let's take off minus 2, put it as a number 1 as a coefficient. So equal to x squared. Let's transfer this one to the, since I have a quadratic here, let's transfer this one into the quinary square. So this one is giving us n minus half quinary square plus 3 over 4. Why this one? Because if I'm going to expand this one, I get n squared as a first term, I get minus n as a middle term, which is good to go, plus the last term equals 1 over 4, plus this 3 over 4 is giving us number 1. Okay, this one, before we proceed with this one, I'm going to put this one separately because I have number 2 as a multiplier. So I get here 2 times is multiplied by n minus half quinary square plus 3 over 2, because number 2 will be multiplied by this one, is giving us 3 over 2 equals x squared. But I see number 2 here at denominator. I'm going to clarify this denominator by multiplying both sides by number 2. Okay, so if I'm going to do that, I will have a number 4 here. So multiplying both sides by number 2 here, I get twice x squared equals this 4. This 4 I'm going to put it inside. This one becomes 2n minus number 1 quinary square plus number 3 here. Okay, so let's go through the substitution. Let's put it, I'm going to put this one as a z. Okay, so I get here 2 times x squared equals number 3 plus z squared. Okay, so I have ended with this nice expression here. Since we see number 3 here, I'm going to reduce this one to my 3. So if I'm going to do that, I get here 2x squared is congruent to z squared mod 3. Okay, let's go through the chart. I get the following values. I get 0, 1, 2, 3, 4, 5, and so on and so forth. Let's put k squared, and let's put 2 times k squared. So let's check the reminders of this one when you reduce this one to mod 3. So I get 0 here. It's clearly 0. It's clearly number 1. I get number 4 here. 4 mod 3 is giving us 1 as a remainder. Number 3 square, which is 9, it will have 0 as a remainder. 4, 16. 16, 1 more 15, which is 1. 25, 25 is 1 more 24. Get 1 0 here. This is enough. This is how kind of repeating 0, 1, 1, 0, 0. This set here belongs to the 0, 1. Let's check the other one. So we'll have the same thing. This remainder will be multiplied by number 2. I get 0 here. I get number 2 here. I get number 2 here. I get 0. I get 2. I get 2. This one go all the way down. This one. So now in order to make the comparison, none of those numbers none of these reminders which we have on the right hand side of this equation equals to the left hand side of this equation except 0, except this one, which means we have a solution at a point 0. Okay, so this one is telling us z and x is a congruent to 0 mod 3. Okay, let's square this one. I get z square is a z square or x square is a congruent to 0 mod 9. So what we have done here, so we are squaring both sides. So this one, if you go back to this one, you are going to reduce the divisor of this one. Okay, so if you square this one, you are going to square the whole thing. Square this one, the module, square this one, square this one. Okay, so we get this one. Now let's go to the original expression. Okay, let's go back to the original expression to apply the same rule that I have here on this one. Okay, let's reduce this one to the mod 9. So we know z square is always 0 here. Z square is a congruent to 0 mod 9, and also x square is a congruent to 0 mod 9. By multiplying this one by number 2, I still have a 0 here. So I get 0, I get number 3 here. 3 will stay the same. I get 3 plus 0 is a congruent to 0 mod 9. Okay, so get here 3 is a congruent to 0 mod 9. This one, it's impossible because the divisor exceeded this one. Okay, that's why you cannot have integer here. So this one, 3 over 9 is not a whole number. Okay, since we have ended up with this contradiction, that means it's impossible to have a perfect square. Okay, so I have ended this video. Don't forget to hit the subscribe button and support our channel, and thank you for watching. I will see you next video. Bye.